So we're going to be moving on to projectile motion. And so you'll notice if we look at the path of this projectile of the basketball, that it actually creates a parabola shape. Okay, and so the reason for this is due to the horizontal and vertical forces that are acting upon the ball. Okay, so it's very similar to whenever we looked at falling objects, and if we were to throw a ball straight up and then it would come back down, the way that gravity works on the object is going to be almost identical, or it is identical. And then we're just adding in a horizontal aspect to this. Okay, so the equation for a parabola, if you remember back, is y equals ax squared plus bx plus c. Okay, and so we can break down the kinematic equation if we split up this delta d into the final displacement minus the initial displacement. We'll get, and rearrange the equation, we'll get this d2, which is kind of like the same as our y. Okay, and then we get the 1/2 a. So this would be like an a. So our delta t squared is going to be our x squared plus the initial velocity is going to act as our b of delta t. Remember, delta t is our x. And then we have the initial displacement, which is correlates with the coefficient of c. Okay, so generally we don't break up in physics. We don't break up the final displacement and initial displacement, but it just kind of helps us see how the formula that you normally see in math class is identical to the ones that we're using here. So we've already looked at the motion of freefall objects, like I was saying. So now we need to look at how the adding in the horizontal aspect can change the shape of the projectile. So if we were to throw a football, the path changes depending on, one, the initial speed, okay, and then also the angle at which it's launched. Okay, so all of these paths are modeled by parabolas, and they're going to have different coefficients. So if we look, the initial velocity is equal on these two, okay, but the angle is different. So for the first football here, okay, it is at a higher angle, so it goes less distance, okay, compared to the second one, even though we throw it with the same amount of initial velocity, it's going to travel further because it is at a lower angle, launch angle, okay? And then you'll notice that the last one here goes the same distance, okay, even though it's a lower angle, and this is just because this one has a smaller initial velocity, okay? And so if you're to drop an object and launch an identical object horizontally from the same height, their motions are extremely similar, okay? So if we look, let's just look at the vertical aspect, because we've kind of already dealt with the vertical aspect before, okay? We have, for time 1, we have this distance here. Okay. For time 2, we have this distance for both objects, the one that's following the parabolic shape and the one that's just dropping straight down, because you'll see they're at the same height at the same time. Okay, the next one, T3. Okay, and then lastly, T4. Okay, and so they're going to be progressively getting further distances, horizontal or vertical distances, because the object is accelerating due to gravity. Vertical displacement is the same for both. Okay, and it's increasing over time due to the acceleration of gravity. Remember that gravity is negative 9.8 meters per second squared. The acceleration of gravity is. Okay, now if we were to look at the horizontal movement of the object, okay, this ball that is just being dropped has no horizontal displacement, okay? But if we look at this other one, okay, we have you should see, my lines aren't lined up perfectly, that it is equal. So this is our, so all of these down here were our y, our delta y. So this is all y. So these are each our displacement of x. So I'm just going to put x just for easiness. Okay, so you should notice that the ball launched horizontally travels the same horizontal distance in equal time periods. Okay, so the horizontal displacement is in equal increments over time. Okay, and that's because there's no force acting in the horizontal plane that is causing acceleration compared to the vertical plane. There is a force of gravity acting upon the object causing acceleration. Okay, so we're talking in a closed system. So we do know that in real life, we would have things like wind resistance and things like that that could affect the horizontal velocity of an object. So we're going to go over the shape of the parabola and talk about the different variables that you'll need in order to solve for the different problems that you'll have. Okay, so let's start with the horizontal variables. Our first horizontal variable that we're going to label is delta d of x, so the displacement of the horizontal. This is known as range. Okay, so it's just how far the object travels horizontally. Okay, so here, this will be our range, which is delta d of x. So it's going to be from here to here. Okay. We're going to have our horizontal velocity, so our velocity x is just the horizontal velocity. Okay, and just remember it's constant. Okay, so this is why we don't have an initial velocity and a final velocity of our horizontal x, just because it is constant the whole time, so we can just use v of x. And then the last would be our delta t, which is just the elapsed time. All right, so the vertical variables, we're going to have a bit more to look at just because there is a bit of change happening due to the acceleration of gravity. So let's start first with our delta d of y. Okay, this is our vertical displacement. Okay, the vertical displacement is greatest at the max height of the parabola. Okay, and at the bottom of the parabola, the displacement is going to be 0. Okay, so our max height is going to be here. Okay, and so this is going to be our delta d of y, the max. Okay, and something important to kind of remember or to know is that this is going to occur at half range, so half of the distance of the horizontal aspect and half the time. Okay, so sometimes that can help you when thinking about the problem. Okay, and then we have the initial velocity of our vertical aspect. Okay, so that's going to be at the start. Oops. So I'm going to draw like a tangent line for this. So this is going to be our v1 of y. Okay. Or no, just our v1, sorry, our initial velocity. So our, let me change the color. So the velocity of the launched object is going to be our v1. So in order to get our initial velocity, we would have to find of y, we'd have to find the y aspect of this triangle, which create a right triangle. So v1 of y, and then here we would have our, let me just make them full arrows. We would have our v of x. Okay, and then here we would have theta, which would be our launch angle. So theta is just our launch angle. Okay, and this would be at t equals 0, whatever it is, seconds, hours, minutes. Okay, so for the next variable, we have the final velocity, v2 of y. So this is going to be our final vertical velocity. Okay, and something to note that if it's on flat ground where we have a symmetrical parabola, it's just going to equal the negative or the inverse of our initial velocity. Okay, so that's an important thing to kind of like help create shortcuts for you. Okay, so our final velocity is going to be here. So v2. So if you're finding v2, this would be your v2 of y, and then this would be your vx. Okay, and then our angle would be here, our final angle. All right, the next variable is acceleration, and we know it's negative 9.8 meters per second squared. Okay, so that's just gravity here on Earth. And then also elapsed time. So to start with breaking down a projectile motion problem, the first thing that they generally give you is they will give you the initial velocity of the projectile and the angle in which it's launched. Okay, so the first thing that we really need to do is make sure in breaking the initial velocity into its different components. So whenever we did the component method, that's going to be necessary for setting up all of these projectile problems. So the initial velocity must be broken into its horizontal and vertical components because the different equations are used for the horizontal variables and the vertical variables. So because the horizontal has no acceleration, we're just going to use the constant velocity equation for the horizontal aspect of the variables, okay? For the vertical, there's a constant acceleration because of gravity, so we're going to use the 5 kinematic equations, okay? And both of these equations can be found on the back cover or the back of the front cover of your guys' packet if you need to look back at them, or you can use your kinematic notes from the first chapter. Okay, so define the horizontal and vertical components of the initial velocity. First, we need to draw the initial velocity vector with its magnitude and angle. So here, if we look at the practice problem, we have the initial velocity of 14.2 meters per second, and it looks like it's east 54 degrees north. So from the eastern barrier, it is 54 degrees north of that. Okay, we're going to create a right angled triangle with the initial velocities as the hypotenuse. So our initial velocity of 14.2 is going to be our hypothesis or our hypotenuse. And so I'm going to go ahead and label my Vx. So here, it's kind of hard to see. Here is my Vx, my velocity of the x side, and then my velocity of the y component. Okay, and then we're just going to use trigonometric ratios, SOHCAHTOA, in order to solve for this. So we're going to be using SOHCAHTOA for this. And so for our, let's do our vertical aspect, our y first. So it is opposite our angle of 54 degrees. So we're going to use sine of our angle, 54, equals our Vy over our hypotenuse, 14.2. Okay. And so if we rearrange it, it would be, so we'd time both sides by 14.2. We'd have Vy equals 14.2 times the sine of 54. And we'll get that the Vy is 11.49 meters per second. Okay, and then to solve for Vx, it's the adjacent side to our angle, so we're going to use cosine of 54 equals our adjacent side, Vx, over our hypotenuse, 14.2. Rearrange it, so Vx equals 14.2 times the cosine of 54, and we'll get that Vx is equal to 8.35 meters per second. Both of these will be positive, so you can kind of go through and give them their directions as well. So this would be the to the east, and then this would be to the north, just so you can make sure that you're keeping them positive.